All right, we're getting down to the end of applications of derivatives. Lesson 7 or part 7, because usually there are lots of parts, whatever, is L'Hopital's rule. And you can see there are 3 different ways to spell L'Hopital's rule. L'Hopital's rule is also known as Bernoulli's rule. College Board has started to spell it, this way, with the S, but that doesn't change the fact that French name, we keep that little S silent. L'Hopital's rule. Okay, so you need to know when L'Hopital's rule applies. Our first objective is to be able to use L'Hopital's rule to evaluate certain limits. Not all limits, but this does have to do with limits. And in order to use L'Hopital's rule, we have to write down the prerequisites for using L'Hopital's rule. I suppose unless it's multiple choice. And this is for the kids in my class. Usually it's the boys. They end up saying hospital and then they snicker. I don't know. There's something about 16-year-old boys that make that happen. Okay, so just like any other theorem that we've had, intermediate value theorem, mean value theorem, extreme value theorem, squeeze theorem, although we don't really write much for squeeze theorem, you need to write down the prerequisites if you are going to secure full credit. And I'll show you an example from one of the more recent, I guess it's not that recent, but whatever, one of the free response questions from the actual AP exam. Okay, so we're going to be ending up using continuity a bit, so hopefully you remember the formal definition of continuity at a point. So f is continuous at some x value if and only if. 2 ways to go. I'm just going to write the two-sided version. The limit as x approaches c of f of x is equal to f of c, which basically means, at c, the y values are approaching the same point, and turns out they are approaching the y value of f at c. We could have also said the limit as x approaches c from the left of f is equal to the limit as x approaches c from the right of f, and those are both equal to that y value f of c. So if you're thinking either one of those, great, we're in a good spot. Okay, so the limit as x approaches 3 of x squared minus 9 over x minus 3, we can do this algebraically, and we're going to. Then I'm going to show you where L'Hopital's rule comes from, like the proof of it. And then we're going to come back and do this same limit using L'Hopital's rule to see the power of that. Now, if you can do something algebraically, you should. Either way, the first thing we're going to do anytime we see a limit is check for continuity. And of course, 3 minus 3 in the denominator is 0. But don't forget to check the numerator. X squared minus 9 is also 0, so we're thinking 0 minus 0. Indeterminate form, we can probably remove a discontinuity. So we'll rewrite that as the limit as x approaches 3 of x minus 3 times x plus 3 all over x minus 3. And now, when we substitute in 3.1, 3.01, 3.001, 2.9, 2.9, 2.999, the x minus 3's all divide to 1. So we might as well do the easier, limit as x approaches 3 of x plus 3. And x plus 3 is a continuous function, especially at 3, so we can just substitute instead of actually doing a limit and get 6, right? Remember, we're using this definition. Instead of doing the limit, we can just take that y value. Okay, so that's good to go. And, in a problem like this, you might even be able to do it in your head. You can kind of imagine all of this and just think 6. But I want to have something to compare to. And again, this is, if you can do something algebraically, do it algebraically. L'Hopital's rule involves a lot of writing. So we need to know we're going to end up using this thing. And, well, what does this represent? Well, obviously we have some function f of x. And x is an x value, and c, I guess, is an x value. Probably need another color for this to work. And f of x and f of c are 2 y values. And so, to begin with, we're talking about y minus y over x minus x. Ignore that limit for a second. That's the slope between 2 points. But what does it say? Well, we're going to take this point at x and move it closer and closer to the point at x equals c. Okay, so what is this? This is, oh shoot, I don't have it there. This is f prime of c. This is the slope of f at the point c, derivative of f at c, however the heck you want to say that. Okay, so we're going to need that in our proof. So here's when you can use Hopitals' rule, and after we do this, we'll go back and do a couple of examples to show everything you need to write. But number one, you can use Hopitals' rule when you're doing a limit, and that limit has to be of a ratio of two functions, you know, just like we had. Limit as x approaches 3. It's not a 3. I guess I'm looking at the c. Limit as x approaches 3. So in our case, you know, c is 3. And f of x is a function like x squared minus 9. And g of x is another function like x minus 3. So we have some function. And not only that, the function in the numerator and the function in the denominator, each on their own, have to be differentiable near x equals c. And you'll see why in a second. Hopitals' rule, we end up doing a derivative to easier evaluate a limit. Okay, and it also needs to be the case, or at least in this version, we'll say the limit of the numerator function is 0 and the limit of the denominator function is 0. Sorry, got a phone call. We're going through fires here in LA right now. Anyways, limit of the numerator on its own, x squared minus 9 in our case, as x approaches 3, has to be 0, and denominator has to have a limit of 0. Now, that's not always the case. I'll tell you in a second, but whatever. Okay. And basically that means, you know, if f is differentiable and the limit as x approaches c equals 0, that means f of c is 0. Likewise, g of c is equal to 0. So we'll come back to that in a second. Okay, so we're going to start off with limit as x approaches c of our function f divided by our function g. And the first thing I'm going to do is subtract 0 from the numerator and 0 from the denominator. Obviously, I'm allowed to do that. Subtracting 0 doesn't change values, so good to go. The controversial part of this proof is replacing one of the zeros with f of c and one of the zeros with g of c. But let's go back. We actually just said that, you know. F of c is 0 and g of c is 0. You know, maybe it'll help to think it's something like, you know, replacing this top part with 3 squared minus 9, like we had, and replacing this bottom 0 with 3 minus 3. We're just doing a symbol that means that. All right, let's erase all ink. Cool. Okay. And then I'm just going to make room by putting a 1 under f of c minus, or f of x minus f of c, and a 1 under g of x minus g of c. Still keep our limit out front. And I'm just going to multiply by this big ugly version of 1. I want to multiply by 1 over x minus c divided by another 1 over x minus c. And of course, you know, multiplying by 1 is not allowed, you know, but it does have to be the case. X can't be equal to c. What is going on with this computer? But actually, that's not a problem. We're doing the limit as x approaches c. So we're just using numbers really close to c. You know, c plus 0.1, c plus 0.01, stuff like that. Okay. And so once we bring those x minus c's into numerator's denominator and the denominator's denominator, you know, look at what we have. You know, what is the limit as x approaches c of f of x minus f of c over x minus c? Well, that's f prime of c. And what's the limit as x approaches c of g of x minus g of c over g prime of c? Well, that's the derivative of g at c. That's g prime of c. And so there are two ways you're going to see this written. I guess, I don't know if you want to call it the easy way or the simple way or the beginner way, is f prime of c over g prime of c. But we're going to stick to this second way. We're going to keep that limit out front, and we're going to replace, you know, we started off with the limit as x approaches c of f of x over g of x. And what we end up with is the limit as x approaches c, same stuff, over the derivative of the numerator. I'm sorry, derivative of the numerator over the derivative of the denominator. Which seems like it doesn't work, but you know, the algebra's there. And we're back. Okay, so we're going to redo this same limit as x approaches 3 of x squared minus 9 over x minus 3 using Hopitals' rules, so just so you can have a comparison. Where are we? Click through? There we go. Okay, so the first thing I'm going to start off saying is x squared minus 9 and x minus 3 are continuous. We want to say that so we can take derivatives here in a second. It's one of those kind of, we're basically doing a theorem thing. Now the next thing we need to write down, and we wrote it earlier, we wrote this down, or I did in the proof, as, the limit as x approaches c of f of x has to be equal to 0, and the limit as x approaches c of g of x has to be 0. So we're just writing out, and notice instead of writing 0 over 0 or something like that, never do that, especially not equal to 0 over 0. We're just writing out those individual limits because, well, if you think about this, why do we need to write down continuity? Well, how did we get these limits? We got them by substituting, so we're actually using that definition of continuity. Okay, so we write those out separately, and then we write using L'Hopital's rule. And the reason we have to write something like using L'Hopital's rule, well, notice we kept our limit the same. And it's definitely the case that x squared minus 9 is not equal to 2x, and x minus 3 is not equal to 1, and that's ridiculous. And the other thing is x squared minus 9 over x minus 3, that's equal to x plus 3. So we didn't do algebra. If you didn't have any of this junk in the middle, your work kind of means you think x squared minus 9 over x minus 3 is equal to 2x. And turns out it's not, obviously. But we know this thing called L'Hopital's rule that we can get the same limit by doing the derivative of the numerator and derivative of the denominator. So it turns out that 2x is continuous, so we can substitute. You don't need to write that, but just a good reminder. And we get 2 times 3, or 6, the same thing we got before. Okay. And so the other thing is, I kind of alluded to this earlier, you can actually use L'Hopital's rule in infinity over infinity. And, the plus and minus don't matter, right? Positive and negative version of infinity don't matter. And the reason is this. Let's say we had the limit as x approaches infinity of e to the x over natural log of x. That's definitely not 0 over 0, but this is the same thing as the limit as x approaches infinity of 1 over natural log of x, which does go to 0, right? Because if natural log grows without bound, 1 over natural log shrinks down to 0, and 1 over e to the x in the denominator. So we actually don't need to rearrange, but you need to understand that that algebra works out, so we can just use L'Hopital's rule when it's an infinity over infinity situation. And a lot of times that's the more common one. We can use L'Hopital's rule to compare relative rates of change. Okay, so let's do some examples. The limit as x approaches 3 of sine of x over x. Well, the first thing we want to do is check continuity. And when we substitute in 3, we notice sine of x over x is continuous at 3, not at 0. And so we just write sine of 3 over 3 and we're done. So the examples are we're doing limits. We're not using L'Hopital's rule. The homework I'm giving my kids tonight, there's only actually like 1 or 2 where you have to use L'Hopital's rule. Although I think they're going to use it a lot more. So what's the limit as x approaches 0 of sine of x over x? Let's try that one. Well, the first thing we do, we substitute. We get sine of 0, which is 0, over 0, which is 0. And so this is a great L'Hopital's rule situation. But you should have had this one memorized. This is one of the 2 trigonometric limits that kind of all of calculus with trigonometry is based on. Limit as x approaches 0 of sine of x over x is 1. But let's go through the whole thing. So if we're going to use L'Hopital's rule, we're going to check sine of x is continuous. X is continuous at 0, so let's write that. And again, you might think, but sine of x over x isn't continuous at 0. I know, we're actually checking the numerator on its own and the denominator on its own. Okay, then what? Well, we need to state what we kind of already checked, that the limit of the numerator, limit as x approaches 0 of sine of x is 0, and the limit as x approaches 0 of the denominator x is also equal to 0. What should we write next? We're going to write, hey, we're doing something crazy. We're about to do a derivative. We're going to write using L'Hopital's rule. L'Hopital's rule applies, something like that. And then what is the next thing we're going to write? Well, we're going to keep our limit as x approaches 0, but remember, we're replacing numerator sine of x with its derivative, cosine x, and we're going to replace the x in the denominator with its derivative 1. So limit as x approaches 0 of cosine x over 1, and of course cosine of x over 1 is continuous, and cosine of 0 is 1. All right. Do we need L'Hopital's rule here? Limit as x approaches infinity of sine of x over x. Well, we don't, because the numerator is bounded, this is really a sandwich theorem thing. The numerator is bound between negative 1 and 1, and the denominator is growing. Think a million, a billion, a trillion. 1, 2, 3, 4, 5, 6, 1, 2, 3. Okay, there we go. 12 zeros. And so it doesn't matter if it's 1 over a million, 1 over a billion, 1 over a trillion. You know, that shrinks down to 0. Negative 1 over a million, negative 1 over a billion, negative 1 over a trillion shrinks down to 0. But, you know, sine of x doesn't have to be negative 1 or 1. It could also be like negative 1/2 or negative 1/8 or like negative root 2 over 2 or something like that. And so we can just see, we can think, well, no matter what, that numerator is going to be negative 1 to 1 inclusive, somewhere in there, and that denominator just keeps growing. So we'll just write a limit of 0 and keep the rest of that junk in our head. What about the limit as x approaches 2 of cosine of x over x minus 2? Well, cosine of 2, I don't really know what that is. That's some negative number because 2's between pi halves and pi, but it doesn't really matter that it's negative. So we have some constant divided by numbers closer and closer to 0. That's unbounded growth. Now we're not going to write cosine of 2 over 0, but that's, you know, what we're thinking when we substitute in. But it's really like cosine of something near 2 divided by, you know, 0.1, 0.01, 0.001, which means we're doing things like multiplying by 10, multiplying by 100, multiplying by 1,000. So we get does not exist. All right, well, what about here? Limit as x approaches infinity of e to the x. Well, you know, e to the x, that grows without bound. Limit as x approaches infinity of x squared grows without bound. Which one grows quicker? Some of you should know, and the rest of you are going to see how L'Hopital's rule can be used to check rates of growth. And so we're going to start off real similar. We don't have 0 over 0, but remember, infinity over infinity is just fine too. X squared and e to the x are continuous. We're not going to do limits. We're going to use continuity to avoid limits. Limit as x approaches infinity of x squared is infinity. Limit as x approaches infinity of e to the x is also infinity. So we're going to use L'Hopital's rule and keep our limit as x approaches infinity out front. Numerator is now the derivative of e to the x, which is, of course, e to the x. And the denominator is the derivative of x squared, which is 2x. So now we try again, and we think, you know, what happens to the numerator? E to the x grows without bound. The denominator, 2x, grows without bound. And we kind of already know the answer, that e to the x is growing quicker. We see that concavity in e to the x. E to the x is concave up, so its slope increases, 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 and 2 to the x has a constant slope. But we started off analytically, so let's keep going. And here's something else we haven't mentioned yet. You can use L'Hopital's rule twice. So e to the x and 2 times x are both continuous, and limit as x approaches infinity of 2x is infinity. Limit as x approaches infinity of e to the x is infinity, so we can use L'Hopital's rule one more time. And now we get the derivative of e to the x, over the derivative of 2x2. And limit as x approaches infinity of that is, of course, not a number. So that does not exist due to unbounded growth. All right, last thing as promised. We're going to look at 2018 number 5 to see kind of how this goes. So it really doesn't matter what parts A, B, and C are. But at the beginning, you're given f of x is e to the x cosine of x. And I guess, you know, when you see that, you're supposed to think, holy crap, e to the x cosine of x, I can't combine that, I can't simplify, nothing like that. But you should realize e to the x grows. Cosine of x changes sign, right? -1, 1, and all those numbers in between. And so I guess what I'm thinking, e to the negative, oh, nope, that's not right. Negative e to the x is going to be a bound, e to the x is going to be a bound, and we're going to get some graph like this. But whatever. So in part D, you're given, g is a differentiable function. Hey, here's this new thing. G of pi halves is 0, so that's already a hint. The graph of g prime, the derivative of g, is shown below. Find the limit as x approaches pi halves of f of x over g of x, or state that it does not exist. So that's another big hint that you're given g prime, you're supposed to evaluate the limit of g. So how are you supposed to get there? And the answer is L'Hopital's rule. But then, I think it was 2019 or maybe 21. Then they started giving limits where it pretended to be L'Hopital's rule, but not, so we have to be careful. But anyways, let's see how that's scored. You get 1 point for basically the prerequisites. G has to be continuous at pi halves, and we know that, and they say we need to make that link. You can't just say G is continuous, you have to explain why G is continuous, and based on things you know. Since G is differentiable, G is continuous. Okay, anyways, which means, notice, this is the definition of continuity. The limit as x approaches pi halves of G is equal to G of pi halves, which is equal to 0. Okay? And then, it says the limit's equals 0. You actually need this first limit. The limit as x approaches pi halves of f of x is equal to 0. And notice you don't have to say f is continuous. I think we should, but that's pretty obvious. E to the x is continuous, cosine is continuous, and multiplication doesn't present any issues. So we can see by substituting in pi halves, cosine of pi halves is 0 times e to the pi halves gives us 0 overall. Anyways, and then 1 point for applying L'Hopital's rule, and off the top of my head I can't really think whether we get the point or not. But obviously you can't get the answer without that first point. But notice limit as x approaches pi halves of f over g is limit as x approaches pi halves of f prime over g prime. And either one of these are actually okay. You don't have to have both. But what it's saying there, if no limit notation is attached to a ratio of derivatives, if you just wrote f prime over g prime, that's clearly using L'Hopital's rule. You get that middle point, but you don't get any of the others. All right. Now we're ready for what's next.